So in the previous lecture, we talked about the question about random variation, as well as some of the errors by design that that you can encounter in a current mirror, as well as and then we started a new topic, which is differential amplifier. In the differential amplifier case, we initially looked at the motivation for the differential amplifier, and then followed up with a simple change by adding just a current source at the bottom of two common emitter amplifiers that you can achieve, and how much impact it can make on just amplifying the difference and removing the common mode signal. We talked about that. We also learned about the concept of virtual ground, and so this lecture I'm going to the previous lecture was just to get you introduced to the concept. In this particular lecture, we are going to go dive deep into a lot more mathematical analysis. So be prepared. Keep your notepad with you and kind of walk with me through all the equations. It's kind of important to go through the equations to appreciate how this works. Because unless you really solve the large signal equations, you cannot convince yourself how it works. So today we are going to go through a bipolar differential pair amplifier example, followed by a MOSFET differential pair example. And in both cases, we are going to go through large signal analysis and then write a whole bunch of equations and convince ourselves that it works. In the previous lecture, we did very qualitative analysis of a diff pair, and I introduced the concept of virtual ground. And now we are going to do a large signal analysis of a diff pair. Okay, so let's draw the schematic first. Let's label all the nodes properly. So this is VIP, this is VIN, which is a negative input, and this is V tail. Okay. And then this is VON, because from positive there is an inversion right here, and this is VOP. So we are taking into account the inversion that happens from your base to collector by definition. And here we are ignoring R0 and base current. Using our KVL, VIP minus VBE1, okay, which will be this VBE1 will be right here. That will be equal to V tail, and that would be same as VIN minus VBE2. Okay, so we can rearrange this as VIP minus VIN. That will be equal to VBE1 minus VBE2, IC2 divided by IS2, VIP minus VIN, and this is our equation number 1. Since the two transistors Q1 and Q2, they are identical, IS1 equal to IS2, so this would become VT ln of IC1 divided by IC2, VIP minus VIN. Let me write this as our equation number 1, and then from this you can also write IC1 is equal to IC2 and times exponential VIP minus VIN divided by VT. Okay, so this is one equation that we have. The other equation we have is IC1 plus IC2 is equal to 2 times I. So let's solve it further. Now we can substitute the IC1 in this particular equation, which is number 2, equation number 2, and then we can write it out as IC2 exponential VIP minus VIN divided by VT plus IC2 is equal to 2 times I, and then you can collect the terms and you will get IC2 will be equal to 2I divided by 1 plus exponential VIP minus VIN divided by VT. Okay, that would be IC2. And then if you substitute that in the equation number 2, this back into equation number 2, then we can get IC1, which will be equal to 2I minus IC2. That would be it, right? So then this would look like this. It would come out to be IC1 will be 2I exponential VIP minus VIN divided by VT, and then 1 plus exponential VIP minus VIN divided by VT. So now we get IC1 and IC2, and what are we really looking for? So what we are really looking for is you're applying a voltage VIP and VIN, and you're looking for VOP and VON. So what is VOP? VOP minus VON, that would be equal to VOP is VDD minus IC2 times times RC minus VDD into minus IC1 times RC. Let's make sure I have chosen the correct value. So VOP, yes, VOP should have IC2 and VON should have IC1. All right. So then this equation becomes VDD goes away, and then we get RC multiplied by IC1 minus IC2. Okay, so we can substitute now IC1 and IC2 in this equation, and this will become RC times 2 times I, which is right here. 2 times I will come out from both sides, and then we will get, since we are subtracting IC1 minus IC2, you will get exponential VIP minus VIN divided by VT minus 1, and in the denominator we will get exponential VIP minus VIN divided by VT plus 1. What does this function look like? This function looks like a tan H function. VOP 2 times I RC, and this one we can say it's tan H of VIP minus VIN divided by 2 times VT. So that would be the this would be the tan H function. Let's in this particular case, as we already said, what is VIP minus VIN? That will be our differential input voltage, which is VDM. Okay, so as you can see in this particular function, the output differential voltage is not dependent on common mode voltage at the input. It's only dependent on the differential mode voltage, V differential. Let's look at this particular function and see what happens when VIP minus VIN is much greater than 0. So in this particular case, you can see that the two terms, exponential terms, will dominate, and you will get the answer will be VOP minus VON would look like plus 2I RC. Similarly, if VIP minus VIN is much less than 0, then you will get VOP minus VON is equal to minus 2 times IRC. You can convince yourself of that. So having all this information, now we can plot the transfer function. So we're going to plot here VIP minus VIN, and here I'm going to plot VOP minus VON. Okay, so the tan H function, it it looks like this. So at the end we would expect minus 2I RC here, and here we would expect plus 2I RC. Okay, so when VIP minus VIN is very large, then it should asymptotically approach 2I minus 2 plus 2 IRC, and then here it should approach asymptotically minus 2 IRC. So the transfer function is going to look like this. You will have a really sharp looking curve, and then it will kind of approach asymptotically plus 2 IRC, and I'm kind of bringing this out to your attention because I'm going to make a point later on. Okay, so it will asymptotically reach minus 2 IRC. This is the tan H function. Again, in this particular case, you may get confused and you may say that, hey, you know, if you look at simple bipolar common emitter pair, if I apply a positive input, then you will get negative output, right? I mean, it flipped like this. But here in this case, you're not showing the inversion. We kind of took care of that when we labeled the nodes. So to bring that back to your attention, if you see, we label the node in such a way that the inversion was built into the labeling. So for example, if I have VIP here, then I label this node as VON. Similarly, if I have VIN, which is negative input, I label this node as VOP. So that's why we don't see the inversion in this particular transfer characteristics that we see. So keep that in mind, because if you look at multiple books, multiple references, people look at it differently and then it might get confusing. So just make sure that you have a good understanding of that. We will do a similar analysis for a MOSFET diff pair. So far we had not talked about MOSFET diff pair, so let's walk through that. Here also we have a couple of approximation. We will be ignoring R out and body effect. And we are also assuming that the two, let's draw the circuit first. So in this particular case, we have VDD. The reason I choose to use the current 2I because when the two inputs are equal, then the current I will flow through each side. And that makes our all analysis equations a little bit easier to deal with. This is your RD, this is your RD, and this is your okay, this is VIP, this is VIN, and we said this is VTail, and we have plus minus VGS1 and plus minus VGS2. Again, here in this particular case, we are going to label the nodes in such a way that the inversion is built into the labeling, VOP and VON. So you will have current I1. This is transistor M1 and this is transistor M2, and you'll have current I2 which will flow through the other side. For this particular analysis, we are also going to make another approximation which is Kn. Not approximation, it just make our equations a little bit easy. So we call Kn is equal to mu n Cox W by L of the transistor. And in this particular case, we are saying that M1 and M2 both are matched and they have their W by L. That's what their device size is. So let's write all the basic equations. So here we are going to assume that both the MOSFETs are in saturation, and under that condition I1 will be equal to Kn divided by 2. Remember, this is Kn and it doesn't have divided by 2 that we have in the MOSFET saturation equation. So this will be VGS1 minus VTH square. This would give me VGS1 is equal to VTH plus square root of 2I1 divided by Kn. Let's move on to the next one. I2 VGS2 minus VTH square, which will give me VGS2 is equal to VTH plus square root of 2I2 divided by Kn. So what is our differential input voltage? VDM is equal to VIP minus VIN, which if you look at VIP minus VIN, then you can go around this particular loop here, KVL, from here to here, and you can see that that will be equal to VGS1 minus VGS2. So then you can write the expression square root of 2I1 divided by Kn minus square root of 2I2 divided by Kn. MOSFET equations are a little bit tedious. The typical thing that we do here is we know that I1 plus I2 that is equal to 2 times I. The current between the two branches, it sums up to 2I, we know that. And also we know that let's call I1 minus I2, okay, let's call that equal to delta I. Just a difference in the two currents. So if you use these two expressions, then you can say that, hey, what will be my I1 equal to will be I plus delta I divided by 2 and I2 will be equal to I minus delta I divided by 2. So this kind of tells you there is a common mode current and there is a differential current, delta I being the differential current. We can go back to our original expression, which is for VDM, which is right here. We can go in there and start substituting I1 and I2. Okay, I hope you're writing all these by yourself and getting the hang of it. I can say VDM equal to square root of 2I1 divided by Kn minus square root of 2I2 divided by Kn. So you can say VDM square, that would be equal to, what would be VDM square equal to? That would be square of this 2, which will be 2I1 divided by Kn plus 2I2 divided by Kn, and minus 2 times square root of 2 by Kn I1, and again square root of 2 by I2 Kn. So this you can see it looks like 2 I1 divided by Kn plus, so let's simplify it a little further. You'll have I1 plus I2, these two terms coming together, minus 4 divided by Kn, because you have Kn coming in, and then you have square root of I1 I2. That's what you'll get. So we already know what I1 plus I2 is, so we can substitute that. That would be VDM square will be equal to 2 times 2I divided by Kn, and minus, I would put 4 divided by Kn, and here what I would do is I would make I plus delta I by 2, and then you will have I minus delta I by 2. So now we can kind of solve this equation. This equation will look like I'm going to get the Kn divided by 4 on this side, which will give me VDM square, which will be equal to I minus square root of I square minus delta I by 2 square. A plus B multiplied by A minus B, you get A square minus B square. So that's what this formula is. And now I can start playing with this. I can rearrange this term. So if you rearrange, you will see the rearranging will give you square root of I square minus delta I by 2 square. That will be equal to I minus Kn divided by 4 VDM square. So if you square both sides, you'll get I square minus delta I by 2 square, and that would, this square of this is going to look like I square minus Kn by 2 I VDM square plus Kn square divided by 16 and VDM to the power 4. Now you can probably understand why I did this. The I square will go away, and you will get, now you will only get equation which has VDM, which is applied on this side. You have VDM, and here we have delta I. Delta I can quickly give you VO differential, right, which is VOP minus VON. So that's what we are trying to do. We are trying to figure out exact large signal relationship between input and output. So that's why we did so much math. So let's move forward from here, and you will see. So what do we get here? We get delta I square divided by 4. That would be equal to Kn divided by 2I VDM differential voltage square minus Kn square divided by 16 VDM to the power 4. So then I can group things together, and you would get delta I square is equal to 2 times Kn I VDM square minus Kn square divided by 4 VDM to the power 4. Next, what we can do is we can remove Kn square divided by 4 times VDM square out of this equation. So this would give me Kn square divided by 4 VDM square. I took it out of the equation, and then this part will become 2Kn I divided by Kn square, and you'll get 4 over here also, and minus VDM square. That's what we'll get. So this again gives you We can clean it up a little bit. Let's see what can I clean it up with. So this would look like kn square divided by 4 VDM square, and in the bracket you will get 8I divided by kn minus VDM square. So now we can take square root on both sides, and then you should see delta I will be equal to kn divided by 2 VDM, because we're taking square root, and then this is also square root term, which is 8I divided by kn minus VDM square. So if you look at this expression carefully, this term cannot be negative. So this equation is valid only when 8I divided by kn and square root of that minus, and this is VDM again 8I divided by kn square root. So the V out has to be less than this particular term. It has to lie between these two. Otherwise, the term will become negative, and that's really important. So let's take it one step further, because there is an interesting result waiting after all this crunching that I would like you to enjoy. What's really going on here is there is a stark difference between bipolar case and MOSFET case. Whenever your differential voltage switches, basically if you look at a MOSFET case, okay, let's say you start taking this voltage up and you start taking this voltage down, right? After a certain time, what will happen is transistor M1 will be fully on and transistor M2 will be turned off. Then let's assume that V max is that voltage, okay? So what we are saying is when VDM is equal to V max, when current switches to one side completely, okay? So what that means is your delta I, that will be equal to 2I or minus 2I. We can rewrite in this expression, which is delta I will be equal to 2I, and that will be equal to Kn. So I'm just going to put in this Kn divided by 2. Instead of VDM, I'm going to put it Vmax. Okay, and then in square root term, what we are going to get is 8I by Kn minus Vmax square. Let me repeat that in case you didn't get it. What we are saying is we are applying differential voltage VDM, and what I'm saying is that when I apply VDM equal to Vmax, then the current from one side switches completely to other side, and one of the transistor will be turned off. When something like that happens, the current 2I will flow through one side, and you will get delta I, which will be equal to 2I. So delta I is equal to 2I, and we are going to substitute in the original equation VDM is equal to Vmax, and that's what got us here. So we are trying to figure out what the Vmax value is. If you solve this equation, you will see that Vmax is equal to 4I divided by Kn. So if Vmax is equal to this value, then your current will be completely switched to one side. I will leave that to you for exercise, and it should be fairly straightforward. What this is telling me is then I can use this further substitution. I will get Vmax square is equal to 4I by Kn, and then I can say that, hey, Kn will be equal to 4I by Vmax square. Okay, this is something that I'm going to use a little bit later. So come back to our delta I. Come back to this delta I right here, which is come back to that expression. What is that expression? Delta I is equal to Kn divided by 2 VDM and square root of 8I by Kn minus VDM square. So that's the original equation. Now what I'm trying to do now is I'm going to try to replace things in such a way that I can get normalized value of differential input voltage with respect to this Vmax. Okay, remember Vmax is when the current switches from one side to another side completely. I need to remove the Kn out of this expression. I also and then I want to figure out what comes out. So let's see. So we already know we can substitute for Kn. So Kn would be 4I divided by Vmax square, and then we have 1/2 Kn divided by 2, and then we have VDM, And then in the square root expression, what does this look like? So this looks like this. It's twice the 4i by kn. So this would be 2 times V max square minus VDM square. So now we can rearrange the terms again, and you will see it will look like 2i, okay, divided by V max square, and then VDM, and in the square root we will get 2 V max square minus VDM square. I can remove V max from the remove or pull it out, and what you would get then is 2i by V max square VDM, and then I'm pulling out V max from inside the square root term, and I should see what I would get then is let's bring out square root 2 V max. So this would become a 1 minus VDM square divided by 2 V max square. Now we can kind of again do this. Delta I will be equal to, we can collect the terms, 2 root 2, and then we'll have 2 root 2 times I, and one of the Vmax will go away, and you'll get VDM divided by Vmax, and now it will be very clear to you what's going on. And in the square root, what you're going to get is 1 minus half VDM divided by Vmax square. So what this expression is telling us is when VDM is equal to Vmax, when you substitute VDM equal to Vmax, then you will see exactly the delta I will look like 2 times I. So this particular equation kind of accurately reflects the transfer characteristics. Delta I is equal to 2 root 2 I VDM divided by Vmax and 1 minus half VDM minus divided by Vmax square root of the whole term. We can kind of plot this transfer function, how it comes out. Let's see. So on the x-axis we are plotting VDM, and on the y-axis here I'm plotting delta I. But you know that delta I times RD will give you the differential output voltage. Okay, so for the sake of this discussion right now, let's just do this. So this would be 2 times I, and this would be minus 2 times I. So what I said is that when VDM is equal to Vmax, the current switches completely, and same thing on the other side. Okay, will become minus 2I. So let's see how that looks like. So the plot will look like this. Now, if you remember the bipolar case, right? So in the bipolar case, when we start increasing VDM, then delta I will approach 2I. However, it will just approach asymptotically. Okay, it will never become 2I, technically speaking. In the MOS case, that's not the case. In the MOS case, whenever the VDM comes out to be equal to Vmax, then the current is switched completely. One device turns off, and the other device is completely carrying the current. Okay, so that's the difference between the MOSFET case versus bipolar case. As I said again, one of the transistor turns off, and that's the reason it behaves differently. In the bipolar case, one transistor will go into saturation, the other transistor will kind of get into the cutoff mode. What is the slope of this curve, of the curve at the origin? So I'm applying a differential input voltage VDM, and I'm looking at delta I at the output. So you can kind of think of this as a black box where I'm applying V plus and V minus, and then I have a current which is I plus and I minus, and then I'm looking at the difference between the current. So then this looks like a GM, or transconductance. The transconductance, the GM of this cell would be the slope of this curve at origin. Let's figure out what that value is. So when, let's say, V in or VDM, let's say that's equal to 0. Then what we will get is I1 will be equal to I2 will be equal to I, which will be equal to Kn divided by 2 VGS minus VTH square. This is equal to, it's Kn divided by 2, and we like to call this VD sat square. So what is VD sat? Then VD sat is equal to 2I divided by Kn and square root of that. And now let's compare. There was something similar that we had played with earlier. What was that value? So if you remember, value of Vmax right here. If you remember this particular expression, we got Vmax, that is square root of 4I by Kn. So if we look at Vmax, I'll rewrite it again. Vmax is equal to 4I divided by Kn square root. So if you compare these two, you can tell that, hey, Vmax is actually equal to square root of 2 times VDSAT. And this is kind of an important result. What this tells you that, hey, if let's say you choose the diff pair with a certain current and certain W by L ratios, and let's say your VDSAT value that is equal to let's say 200 millivolts. Okay, pick a number. So then my Vmax, this Vmax value, differential pair input differential pair voltage, is going to be equal to root 2, which is 283 millivolts. Okay, so when I apply VDM equal to 283 millivolts, then what you expect is you would have a complete switch of the current. So here you will see the current will switch completely in this particular case. Let's go back to our original equation to get some more insight, which is delta I, that is equal to 2 root 2 times I, again VDM divided by Vmax, and square root of 1 minus half VDM divided by Vmax and square root. This kind of function looks like x multiplied by 1 minus x squared divided by 2, something like that. So this is what that transfer function looks like, right? Since we have square here, if x is much smaller than 1, if x is much smaller than 1, then this term will look like x. Okay, so we can also say that, hey, my delta I will look like 2 root 2 I, and then VDM divided by Vmax. And this is true when VDM divided by Vmax is much smaller than 1. This is kind of where you are approaching that origin point, right? So now I can say that delta I divided by VDM, which is, what did we say, what is delta I by VGM? That would be your big block GM, the transconductance of the big block, because you have output current and you have differential input voltage. What is that equal to? This will look like 2 root 2 I, and then divide by Vmax. Now we already know what was the Vmax value, 2 root 2 I and divided by 4I, and here was the square root of Kn. Okay, let me rewrite this so that you're not confused. Okay, that's our Vmax value. So this is equal to root 2 and then you have root I and you have root Kn, which is equal to square root of 2 Kn times I. What is this value then? This value, square root of 2 Kn I, is equal to 2 mu n C ox W by L times I, and square root of this, right? So this GM of the whole differential pair, you can now tell that, hey, that is equal to GM of each transistor. That's the key revelation out of these equations, is that the slope at origin comes out to be GM of each transistor. You would use that, when you do further analysis using this differential pair. I will stop right here.